For centuries, physics had one unspoken rule. It didn't just predict what would happen, it explained what was. A particle had a position, a wave had a shape, and when something happened, physicists could tell you why. But that rule broke in the early 20th century, not because the physicists made mistakes, but because their experiments worked too well. And then, in a famous experiment known now as the double-slit experiment, particles of light, or photons, were sent one at a time through two narrow openings. If the photons were just particles, you'd expect to see two lines of detector hits, one behind each slit. But even when one particle at a time was sent towards the two slits, the interference pattern appeared. Bright stripes where the waves added together, and dark stripes where the waves cancelled out. One particle at a time, behaving as if it had passed through both slits simultaneously. But when they tried to measure which slit this wave had been through, something startling happened. The interference pattern disappeared. Nothing had physically touched the particle, nothing had disturbed its motion. The only thing that had changed was the question that was being asked. To picture this, imagine tossing a coin. If you don't look, it somehow lands on both heads and tails at the same time. But the moment you peek, suddenly it snaps to one of the two outcomes. That's a flavour of what the physicists were seeing in these experiments. But this wasn't a flaw in the experiment. This result was real and easily reproducible. So physics faced a choice. Either particles didn't have definite properties like their position until it was measured, or the measurement itself was doing something that physics couldn't describe. For a while, physicists tried to keep both realism and consistency. Einstein insisted the theory of quantum mechanics was incomplete, but Niels Bohr took a different approach. He argued that the problem wasn't with the experiments, it was with the questions that were being asked. He thought that physics was not about describing reality as it is, but that it was about predicting the outcomes of experiments. If asking what a particle really is leads to contradiction, well, the question has no place in physics. And this position became known as the Copenhagen interpretation of quantum mechanics. It didn't claim that particles were waves or that waves were particles, it claimed something more radical. Physical properties don't exist in a definite way until they're measured. And physics should not attempt to describe what happens between these measurements. And the Copenhagen interpretation worked spectacularly. Predictions matched experiments to unprecedented accuracy. New technologies followed, semiconductors, lasers, and everything else built on quantum mechanics. But something had quietly changed with the introduction of the Copenhagen interpretation. Physics stopped trying to describe the underlying reality. Students were taught how to calculate outcomes, not to imagine what might be really happening. Questions about what is really going on were not asked anymore. Richard Feynman later famously said that nobody understood quantum mechanics, even those who built it. But this wasn't embarrassment, this was relief. The contradictions had been contained, the equations worked, and the discomfort was pushed aside. Since the introduction of the Copenhagen interpretation, other interpretations of quantum mechanics have been put forward. And these aim to gain some intuition into what's really going on behind the scenes. Some interpretations try to restore realism at the cost of strangeness. Others preserve locality at the cost of intuition. But there is no experiment that can distinguish between these different interpretations of quantum mechanics. Because in these experiments, all we can learn about is the outcome, not what happened in between the measurements, if that question even makes sense. Today, physicists can predict experimental results with incredible accuracy. But when asked what a quantum system is, instead of what it does, there's no agreed upon picture of reality. But this isn't because physicists failed, it's because they succeeded. These experiments in the early days of quantum mechanics left no room for what we call a classical interpretation. There is no reasonable way to picture what's really happening. So rather than abandoning the theory of quantum mechanics, physics abandoned the need to understand exactly what's happening. The predictions of quantum mechanics are real, and the results are real. What lies underneath, if anything does, is something that physics has learned not to talk about. If you want to know more about the most famous discoveries in physics, and about those who discovered them, this might be the channel for you. So like the video and subscribe for more.